Hey everyone, thanks for joining. Just fix this. Okay. So yeah, thanks for joining my stream. Tonight I'll be continuing to work on the Vectrex emulator. So a couple nights ago, actually had a pretty good night, implemented a ton of CPU instructions. I did the complement, multiply, SEX, rotate left, rotate right, exclusive OR, long branches. Hey Fred, welcome to the stream. So yeah, and when I left off last time was on this decimal addition adjust instruction. So I started reading about it and thinking about how to implement it. I think I'm just going to try to implement it the way it's described here and see how that goes. I don't know. I think it should be okay. And even if I get it wrong, I don't think it's going to cause major problems for now in the emulator. I'm not sure if it's, it's usually used to calculate scores and stuff like that, and perhaps at worst it'll just not calculate the score correctly and move on. And then eventually it's something I can try to fix later. So let's see how this goes. So yeah. Last time I think I just added this, but I don't think I added a call. No. So if we go to the opcodes file, decimal addition adjust. So that's just, there's only one of these. So let's go to our table. Let's see, where should I stick this? Yeah, let's put it here. Oh, these are the long branches. No, yeah, it's fine. So we'll call it here. All right, so remind myself a little bit how this instruction works. So we take the value in A and we want to correct it with the CF as a correction factor as follows. So the CF of the most significant nibble and the CF of the least significant nibble. And so I guess what this is, because this accumulator is an 8-bit value, and what I want to do is I want to construct an 8-bit with, does that make sense? Yeah, basically with a high nibble and a low nibble constructed by the rules that are defined here. Okay, so let's start by extracting the nibbles. So least significant nibble will be A and the most significant nibble and I need to shift it right by 4. Okay. So CF LSN, correction factor. So it's going to be equal to 6 if the half carry is set. If half carry is equal to 1, or if the least significant value is greater than 9, then it's 6. Otherwise, 0. The correction factor for the most significant nibble says that it's 6 if the carry is 1, or the most significant nibble is greater than 9, or both MSN is greater than 8 and LSN is greater than 9. Okay? Greater than 8 and LSN greater than 9. Then it's 6, otherwise it's 0. And now that I have that, we add into the accumulator CF MSN shifted left by 4, ORed with CF LSN. Actually, I'll just store it in an adjust value. Okay, now for the condition codes. H is not affected. Set if, so negative will be set if the MSB of result is set, yeah. This book is super inconsistent. But that's the result. V not defined, and C. So carry. Carry is set if the operation caused a carry from bit 7 in the ALU, or if the carry flag was set before the operation. Right. So actually, if I want to do this correctly, I think I just need to do, instead of doing the addition like this, I can probably just call my my addition function. Add impl, I think it was called. Yeah, I have 2 of them. Let's see. Because that should set the same flags correctly. let's see, it will calculate carry correctly, although it doesn't do the part of setting it if it was already set before the operation. Okay, so I might just handle that specially. It says overflow is not defined, so that's kind of a special case. Okay, so maybe in this case, it's not actually worth calling add input because although when it says that overflow is not defined, then I guess it's okay to calculate it. But yeah, maybe it's not worth it. Here, we'll just do it special case. We'll result, say U16 of A plus actually I don't need to do that. Just do A Just thinking about how this is going to do 8-bit, like 8-bit addition, and I won't actually correctly compute carry unless I cast at least one of these up. Like this. Good old overflow. Yeah. So it's kind of good. I'm revisiting the work I did before and realizing that it's garbage. All right, so now I'll just do it correctly on this side as well. Plus U16 adjustment. All right, so now like that on result instead. Oh no, and now I want to store it in A. Okay. So now on calc negative on this, calc 0 on this, but for the carry I want to do if carry was already set, or if it wasn't already set. So I'll do this, if it was equal to 1, or what? Or calc carry on result. Is that right? Yes. And I'm being careful to use the 16-bit result here to know if it actually overflowed. If the 8-bit addition overflowed, which is what I do up here and up here. No, sorry, here. Maybe I should call this R16 just to make sure it's more consistent. In fact, I'm completely inconsistent. Sometimes I use static cast and sometimes I don't. I prefer to use my little const expr helpers for these casts because I do them so often in the CPU that it's just more convenient. Okay. So let's see here. H is not touched. Negative set of the MSB, yeah. Z if all the bits are clear. Overflow is not touched, not defined. And for the carry, cause the carry from bit 7 into the ALU, or if the carry flag was set before the operation. That should be it. So let's see if this gets called when I debug it. All right, let me get my trusty initial values and then we continue. Shouldn't take too long. Okay, let's see here. Just wondering where I'm at. Still in the BIOS. I know that because we're still in the F range, which is BIOS. Ah, and here we go. We hit our breakpoint. Yeah, let's just make this full screen. Okay. So here we are, we're executing this DAA. All right, so here's A. Let's look at it in binary. That's cool. So it looks like we have 8 in both the low and in the high. So I guess that's 88. So Fred says, these moments where it looks like it's doing something are great. You wonder where it's at and what it's doing since you can't see much output yet. Yeah, so true. I cannot wait to actually see some output though. Like I can't wait to start actually rendering what the beam is doing. It's gonna be really cool. It's a bit more tricky actually than when I was doing the NES emulator, because I remember for the NES, because it's all like character tables, I remember just drawing out like patterns for what was being drawn, like, you know, for the raster, and I remember just drawing them into a text file, and I was actually able to see that, like, the very first time I saw something was in my text file. It said Donkey Kong, because I was trying to run Donkey Kong first, and because, you know, it's just a grid, you can actually see that if you just put, like, you know, draw values, like the memory values. I think I was just writing out memory values, and I could see the shape when I zoom out of the dump, and yeah, it was like a memory. That's it. I'd done a memory dump, and I could see Donkey Kong being written in the, what's it called again? It's been so long. Like basically in the video memory. Before the Vectrex, it's a simpler machine, but I have to actually draw vectors, so it's a bit more tricky. Yeah, object RAM, or, well, actually that's for sprites there, but basically the tile RAM. I was drawing like a dump of the tile memory. So here, yeah, exactly, no such luck here with the Vectrex. Okay, so here it would seem that the value 88 is presently in the A register as decimal values. And this is supposed to adjust it. And in this case, it should actually do absolutely nothing to adjust it. So like, let's see here. So that's it. The correction factor is 0 for both, which is what we expect. So R16 remains the same thing as A. So A doesn't change, and we actually are considered negative. It's so funny how this adjustment will even set the negative flag. Like, why would that matter if you're writing decimal values? It's not really negative. Anyways, I guess that's the instruction. Maybe it was simpler to do this in the hardware because it's doing an addition. That's probably what it is. Probably because it has to perform an addition, it uses the same hardware as it does for normal addition, which is why it ends up setting things like all the arithmetic operations, although it doesn't set overflow, or it says, at least it says it's not defined. So maybe it is set, but not necessary. I don't know. All right, 0 is not set, and carry is not set. Makes sense. And now I'm called with perhaps more interesting values here. Well, no, just 6 and 3. I wonder if it'll get called with interesting values. 8, 8, 6, 3, 10 and 4. So this here would need to adjust for the least significant. So if it goes to 10 here, that means that it was 49 and now it's 4010, so technically it should become 50. So let's see if that's what happens. So, okay, so we want to add 6 to the least significant and 0 to the most significant. Okay, so the adjustment value is plus 6. So then R16 is 80. Let's see here, R16, shift right by 4. There you go. And R16 and 0xf, we get 50. So that works. So 4010 became 50. So that adjustment worked. All right, here, let me just do this. A, shift right 4, and A, and 0xf. And now our number is 14 in the upper and 10 in the bottom. So that, I guess that should give us 15. No, wait, 21. Does that make sense? Oh, right, because so 14, it needs to be adjusted as well. Oh, no, sorry, wait. What does this mean? R16 ended up being 336. So what does it mean that when it came in, we had 14 and 10, right? Decimal, these are supposed to be in 0 to 9 range, I think. Let's see. So we had to add 6 to both. So why do we have to add 6 here? Carry wasn't set, but this was greater than 9. And we have to add 6 to the bottom. I guess that's right. Okay, so let's just keep going and see how far we get. Ah, so there might be something wrong. We're getting a read at an invalid address again. Let's see what's this look like. 3409. So that looks like it's in the cartridge space. Why is that invalid? Is that invalid? Oh yes, this happened before. We shouldn't actually be reading in the cartridge RAM because we're running, we don't even have a cartridge loaded. Actually, we do have a cartridge, but so this comes kind of into the, I don't know if I'm missing something because I am loading technically a cartridge, but I don't believe I've told the BIOS that, so the BIOS doesn't even really know. I don't know how it's supposed to know. Probably when you insert a cartridge, there's something in the hardware that maybe sets in the interrupt vector table where to jump to when it's time to play the game. Now, in my case, I didn't do anything, so I think that the BIOS just ends up jumping to the built-in ROM, which is Mindstorm, and shouldn't be accessing cartridge memory. And this is possibly related to the fact that there might be something wrong with this code. Or not. But the only way I can know is to actually run with a full trace to see where we get, as I've done in the past, which unfortunately is a little bit slow. I have here a batch file that I used last time. So yeah, let's run this. Run.bat and output into output.txt. So just let that run. Actually, I had a thought when I did this last time, which is that it might be a lot faster if I run this in release. I don't really need this to run in debug when I do this kind of tracing. I mean, I don't know how much faster it is, but there's got to be a lot of slowdowns going on because it's completely not optimized. Okay, so this is release. Let me just change my, my batch file. Save that. Okay, let's try this. I'll bring this here. My output file is not changing. Or is it? Oh yeah, okay. It's just Explorer not refreshing, or had to wait till the file flushed bytes to the file. Okay. So hopefully this won't take too long in release. So while that runs, I'll just take another look at this code here. Just thinking about having 1610. And so then basically this 10 becomes 0, and that becomes 17. And the fact that this was 16 means we need to add 6. So I would think then this would become 22 plus 1, 23. When adjusted. So it's like 16 plus 6 plus 1. I think that's right. I don't know. Actually, wow, what I can do is I can try that online emulator. Even though I don't have, I can't completely trust it. I actually reached out to the author, and because I had found a problem with it, or I thought I did anyway, and he seems to think it might be a bug as well with the compare instructions for compare for the accumulators. So yeah, he said he wrote it himself and that he would take a look at it. But anyway, in the meantime, let's see how the adjustment instruction works here. So let's do this. If I wanted to write plus does this make sense? 266. No. No, it's just F and A. Yeah, that's it, sorry. Oh, I didn't have 16, did I? Can't be. Let me try this again. While the other thing runs in release, I can run this one in debug. So this might actually affect my stream because I now have 2 instances running. My CPU is at about 90%. Okay, it should be okay. How are we doing on the command line here? Okay, so I hit my breakpoint. So this is the case where A was 136. So that's 8 and 8, so there's no adjustment here. Three and 6, 8 and 8, 6 and 3, and then 10 and 4. And this is the one where I saw that it became 10 in, oh sorry, in the Ellison. Okay. Oh sorry, it's 4 and 10. That's it. This is the one that became 50, or 5 and 0. Yeah. Okay, this is the one, 14 and 0. This would have been 14 plus 6 plus 1. That, so it was 21 that I was getting. 21 decimal, of course. This is all decimal. Okay, so the range really is up to 16. So that's the thing, right? 21 doesn't make any sense. Because it's 16-bit, of course. I need to cast this. So let's say to uint8t. Okay, there we go. So basically this ends up overflowing. What was 14 and 10 became 5 and 0. So does that make sense? $21. Yeah, 21 modulo 16 is 5. And then this should set the carry. Negative, 0, and then carry is set. Because calc carry would have returned true. Yes. Anonymous namespace calc carry returned 1. Okay, so this makes sense, at least from this perspective. Okay, so I'm just going to kill this then. Let's see where we're at on, so this is still running. We'll just do a little tail on that file. Not that kind of tail, like this. Looks like we're still in the BIOS. It's so incredibly slow when I run it with full trace. Maybe what I could do is like make a little condition that says turn on trace once we reach the E range. How big is my file getting now? Let's see. Vectrexy. Oh boy. Yeah. That's a big file. Okay, I'm gonna kill this. This is way too big. Yeah, I think a 1.4 gig file is kind of pushing it. Let's delete that. I'm curious. Let me try something. I'm gonna try something. Disable the trace. Let's put a breakpoint on E000. Because I imagine, since that's the first instruction of Mindstorm, that it should start break there at some point. No, never stop there. Okay, so we're doing a load instruction. So let me get an idea of what our PC is. Oh, PC is F412. So this is probably a BIOS routine. So Fred asks, is this running with like full debug assertions? Yep. But see, I tried to run, I ran the release build, so everything disabled and optimized, no assertions, and dumped to a file, and I ended up with a 1.3 gig file when I decided to stop the trace. Yeah. And I just tried putting a breakpoint on E000, thinking that it would actually start there when it runs Mindstorm, if that's what it's actually doing. But I'm not hitting that breakpoint, and I'm now getting this illegal load that's happening. Post code. What's post? So getting stuck in some kind of post code, says Fred. So either it's running the game or it's stuck in a loop. So, oh, power on self-test. So, I mean, I'm further along than I was before, and the clues from earlier seem to indicate that it's running Mindstorm at some point. So I'm, should be well past that, and I'm just, after implementing this last instruction and continuing, I'm now getting this. Now I've often had these errors where it's accessing out, in areas and ranges that are surprising. Like here it's accessing cartridge space, which, I am loading a cartridge, but the BIOS doesn't even know that. So Maybe I should look at how that works. But the last few times this happened, it's because something was wrong in the CPU and there's a bug and it ends up trying to access an illegal address because there's like a bug in my CPU somewhere. So that's my first suspicion. The thing is that it's hard to debug because, as I did last time, I want to trace the instructions up to that point, but my trace output ends up being huge and very long. And if I output it, it's really slow. So I'm thinking of different things. Like, okay, one thing I'm thinking about is, what if in my debugger, I just put a conditional breakpoint on when or in the CPU actually, on when the PC enters that range, because I know it does. Yeah, you would put in a hack to turn on trace after 1,000,000 instructions. Yeah, so I was thinking, well, yeah, exactly. And I was thinking, what I'll do is I can put breakpoints. So if I can know what's the first E address that it enters, I think that would be a good place to start. Yeah, I just have no idea how many instructions. And what actually could be interesting is you're just giving me a good idea. What if I just have a counter? How many instructions have executed? And then I could totally use that with what you're saying. I can use the concept of having a counter and saying run that many instructions, and then yeah, that's actually a good idea. You would output like in your trace, you would say you'd have a counter for every instruction, which instruction it was. Yeah, that's super useful actually. Yeah, I like it. I'm gonna add that to my debugger. What do I call it? Instruction count. So actually at this point, since I have these two calls, I might want to bring those two to one. Actually, I have 3 calls. So yeah, I'll do an execute instruction here. Where I grab the CPU and call execute instruction and increment my count. Maybe I'll make this big. I think 64 bits should be big enough. Oh yeah, and I got to return the result. Okay, so let's run this again and let's see what our instruction count is. Thanks for the idea, Fred. It's a good one. Oh, okay. So let's see. What's my debugger saying? It says really 10 million. Is that right? It's not bad. 10 million instructions later. Okay. So what I'll do now is I'll just put a conditional breakpoint in here. That should be pretty fast, actually. So I want to break when the instruction count is, say, I'll get about 6. That's 72. Let's give it about 1,000 or a few thousand. Here, 6,000 instructions. Settings, condition. Oops. So Fred says, hope it helps out in the end. It will. When I hit that conditional breakpoint, I'll turn trace back on, and hopefully I'll get something out of it. Did I not set my... I think I have 1 0 too many, maybe? No. Did I put in the wrong place? I might have. Yeah. Okay, yeah, the issue is that I have this, while CPU cycles left loop in here. So I need to put it in the execute instruction. Yeah, not in that loop. It's here. So I have this inner loop for executing as many cycles this frame as it has to execute, so that's why I'm not hitting my breakpoint. I'll need to put it in here, which makes sense. Let's do this. Can I change this to line 566? I like that. should hit that breakpoint soon, hopefully. Come on. I wonder if it's slowing down because of the conditional breakpoint. It shouldn't, but I mean, this is a lambda, so it's possible that I'm not getting the usual speed up of checking data members, but then again, it's not a local variable or anything, so sure spends a lot of time in this range here. Yeah, there it is again. What I might do actually is add something to my debugger where I can say like execute n instructions. That could be useful actually. In fact, I think that is actually something that GDB does support. Step count. Yeah. So I could totally add that. I could add a count to my step. And then it'll stop. In fact, I'm pretty sure that was my plan originally. I have to, hold on, I'll just go off on my second monitor for a second. Okay, so this was where I was documenting my debugger commands. And yeah, step. No, I had not put it. This is like when I was planning out what my debugger would support. And the bold is what I've completed. But I really should do step, and if I pass an optional parameter, it would be like the number of steps to take. That would be good to do. Put a little comment here. Add comments. Add number of steps, optional parameter. So I'm getting from the fact that it's taking so long that putting a conditional breakpoint is making it slow. So what I'm going to do is, for now, I'm going to put a little static here, static debug count. So if it's greater than 0, and this is greater than or equal to it. Should have like debug break, but for now I'll just put a breakpoint on something. Okay. So the idea here is that rather than put a conditional breakpoint in Visual Studio, which seems to not be going quickly, and probably because it's inside a lambda, and in debug mode maybe it's not optimizing it properly. What I'll do is hold on. I'll say, just make sure this is right. Yeah. I'll set my debug count here to this value and have just a normal breakpoint. So hopefully that will be faster. Usually normal breakpoints are way faster than a conditional breakpoint. So let's see how that goes. So we're at 6.3 million instructions. 6.3 million, and we're looking for about 10 million, so we're almost there. And here we go. Definitely a lot faster to do it this way. So I'll set my debug count back to 0. And let's break into the debugger. Okay. I'll turn trace back on. So yeah, see here we are in the E range. Don't know how we got here, but here we are. Makes me wonder if it's even valid. Maybe I shouldn't even be in this range. So what is this assertion? This is not the same one I was getting earlier. What's going on here? Relative addressing. Long branch if equal. So Fred says, oh, okay, you're falling asleep in your chair. Thanks for sharing your journey. We'll talk to you soon. Thanks for hanging out, Fred. All right, so it could be that my assertion is just incorrect here. Good night, man. Let me just see if this makes sense. So this is addressing mode relative. Yeah. Let me see something. If I go to my opcodes here and I look for relative, so that's all the branching instructions here, but branch the subroutine as well, of course. But it's also now the long branches, and of course the long branches are not only size 3, they're now size 4 because they actually include a 16-bit offset, not just an 8-bit offset. So what? But I was assuming that that's what this meant. 2, 2. This is actually 4. Oh, right, because this is in the next table. And so there's one byte, that the very first byte, that says go look in this page, this opcode table. So this is extra byte. For everything that's not in the first table is this extra byte. So actually this should be 4. And in that case, the operands of the instruction right, and the way I do it is in terms of operands, I don't put the that first byte, right? Let me just see what I did here. It's been too long since I've looked at this code. How do I build this instruction? So I have this nice function somewhere at the beginning of this symbol op, I believe. Read instruction. Okay, so it's all done here. So okay, that's it. So if it's an opcode page 1, I store that here, and then I read the opcode byte. And I don't store the fact that it's an opcode page 1, which means that the first byte was 0x10, and for opcode page 2, the first byte is 0x11. And I just discard that byte. I don't really care about it. So I read the next byte, that's my opcode byte. And I look it up, and then for my instruction, to build an instruction, I need to give it the op that I just found. I give it the op page, so if I care about it, it's in there. Let me just take a look at instruction again. It has op page and then operands. So for operands, I then proceed to read as many bytes as I can store in operands, which is 3. I just read 1, 2, 3. And then it depends on the instruction whether or not I care about those. So in the case of a long branch, it will be just the next 2 bytes. So if I come back to my assertion, yeah, I need to assert here that actually the op size is 4. It's technically 4 because of that extra byte at the beginning. This was just a sanity check to make sure that for relative addressing, when we're this is for me and my debugger to know, is it an 8-bit or 16-bit? So I mean, I guess another way I could have done this is not look at the size, but rather look at the page that it's coming from. Maybe that would just make more sense. Because if it comes from page 0, as I saw here, if it comes from page 0, it's always, yeah, in fact, I have long branch always in here. So I even have long branches in page 0, so I can't use that. Oh, that's what the 3 bytes are for. Okay, because it could be a long branch in page 0 or a long branch in page 1. This is the first time I get a long branch in page 1, I suppose. I think. Or at least it's the first time I disassemble a long branch in page 1. That's what it is. Yeah. That's exactly what it is. So, actually, it can be 3 or 4. So let's just say greater than or equal to 3. In which case, it'll behave exactly the same way. Could be a long branch from page 0 or page 1. 3 bytes, 4 bytes. Don't like that formatting. Let's do that. All right, so now I need to redo the breakpoint. My debugger here. I'm gonna make this equals. All right, let's get this started. Oh, wait a minute. Something's not right. There's a build error. PDB corrupt. Wow. Okay. And let me set back my instruction count here. So let's see where we're at. Okay, we're almost there. Here we are. Once again, let's do break into debugger. True. Let's turn on the trace and let's continue. Okay, that's much better. Not hitting that assert anymore for disassembling the 4-byte long branch instruction. And I'm just looking here, while it's running, I can see that we're in the BIOS routines here because we're in the F ones, and then every once in a while I see like an E instruction pass. I think. Yeah, I just saw one. So it's like we're in the game. Ostensibly we're in Mindstorm, and then Mindstorm is calling some BIOS routines, and then it comes back. I think. No way for me to easily validate this. And then we crash here. So let's see what is going on here. So actually here we can see EA94, EA96, EA98. Looks like it's basically getting ready. Yeah, it's getting ready to call a BIOS routine, which is draw VLPB. So let's take a look in the BIOS file that I have here, what that refers to. So here are a couple of functions that actually jump to it themselves. So this routine draws patterned lines using the vector list pointed to by the X register. So here we can see just before calling it, there's a load X of 2S, which is going to be CBE1, which I think makes sense. Memory map. Yeah. Basically, anything that's in the range C800 to C87F and CBEA to CBFE are used by the BIOS for housekeeping, it says. So I guess that makes sense. That it's loading into X CBE1, maybe. Maybe. What else? The vector list has the following format. The list is terminated by a pattern byte with a high bit cleared. So entry DP is D0. Is that true? Let's take a look. Yeah, DP is D0. breg has a scale factor, 214. Seems like a pretty big scale factor. xreg points to the vector list. When we're exiting, so we're not exiting yet. So we jump to the subroutine, we store B04, and then what? What's the next instruction? It's just a disassembling op bug again. It's probably just a disassemble op bug. I really wouldn't be surprised. Let's see here. We're in the process of disassembling it. What's the operation we're disassembling? So it's an indexed mode. Okay. Index mode is usually where we get some trouble. It's a load D instruction. So you can see here, it wants to, the instruction that we have here is it's load D indexed on page 0. Okay, so now we're in the process of disassembling it. And as an effective address, we got something funky. Something surprising anyway. And it's surprising because it's in the address range of the cartridge space. Let me just take a look at the BIOS code before I go further. So what does it do? It says store into B. No, it says set the scale factor. So it's saying store B via T1 count low. I don't know what this means when there's an angle bracket like this. I think what it means is, I think it has to do with the fact that it tells the assembler to use the direct page register, saying, I know that the direct page register has D0 in it. The DP has D0, so subtract this value from it and just store 4, which is what we see here. Like use a direct page addressing mode with offset 4. So I think that's what it means. So yeah, so saying write the value in B to this register, okay? And then we fall into draw VLP. This routine draws the pattern lines. Okay, so this is the one with scale. Okay, I see. But actually, oh no, sorry. So we're here, and then we fall into this one. Okay, this is B. Set the scale factor. What's the difference here? This one says scale. Okay, so this one actually loads the value for the scale from X. This one here just says use what's in B. And then we come here, get next coordinate pair. And that's the indexed mode, saying read what's in X and add 1. So what is an X? Yeah, that's exactly what we're computing. This plus 1 is the address we're trying to read. So the question then is, what is wrong here? Is it that X, does X have a wrong value, an invalid value, or what? So actually the load X is right here. 2, S, so that's indexed mode as well. Load index register. So what happened here? S, which is the stack pointer, the system stack pointer, right? Had CBDF in it. So saying go there plus 2, read the value there, which is 34. It's actually not, this is not the only value, because X is a, it would have read 2 values, yeah, and I'm not showing it in my debugger here, because when I do the commenting, I only show 1 byte reads, but in this case, we're actually going to be loading 2 bytes into X, because it's the 60, I should probably do something about that, like the text when it's a load for 16-bit and actually show the 2 values we're going to load. But we know that it read 34, and then at CBE2 it must have read 08, because that's what we see in X here. 34 followed by 08. So does that make sense? why use the stack pointer? Let me see if I can tell by looking up a bit higher if S is set somehow. Here and here. This looks all wrong. CC. Doesn't seem right. But it's not. This is not affecting S. There's a push S here. So this is probably related. We have another push S a little bit further below. So I guess what it is that we push, probably the code is pushing to the stack values, and then it's going to access them from the stack. Except what I don't understand is that it would mean that when we push, let me remind myself how if push actually decrements the stack pointer, which means that adding to it would be the way to access the values just pushed. So this is push 16, yeah, minus stack pointer. Okay. And push 8 is the same thing. So that's it. So when we push, we can access the values we've pushed by indexing the stack pointer. Okay, so let's look backwards from here where we did load X to S. We also did load B 1S. So we're saying that we must have a push, the nearest push to S. We have pull here, so this undoes the push from there. And then we have this push all the way up here. Okay, let me actually copy this into a text file so I can make some notes. Okay, so what I want to note is that here we are loading how do I write this? We're loading what are we loading? 3408. 3408 into X. We only see the 34 here, and basically it's stack pointer plus 2. So Chase Gayton, think I said that right, is following me. Thanks for the follow. Did I miss like the like on-screen notification of that? Or did it not play? It should have played.
Yeah!
Oh, there it is. I got a notification by email sooner than it showed on stream. So yeah, Chase Gayton, thanks for the follow. Appreciate it. This Twitch viewers list is really strange. Anyway, okay. So where was I? Yeah, so we're loading this value into X from here, and like I said, we're basically offsetting from the stack pointer. Same thing for B here. We're getting D6. So here, loading D6 into B, which is our scale factor. This comes from the stack, so this is stack S plus 1. And this would be S plus 2. And then reads 2 bytes. Yeah, from it. Now let's follow this. If we come backwards, this code here. So as we noticed, so this is branch, but it's not what I'm interested in. Where's the push that I saw earlier? Push and pull. Okay, so here's pull, and this pull goes with this push here. So I don't care about that because this basically undoes what the stack did here, but there is a push right here, A, B, and X. So this is interesting here. So this, and yeah, so if we're pushing A, B, and X, and if I recall, the order is always, it's what we see here, A, B, X. So it'll write A, move the stack pointer back, then B, back X. So that would imply okay, wait, let me just double check what push looks like again. So no, it's actually pushed in reverse. So if we say ABX, it'll actually push X before it pushes B and before it pushes A. So it might actually be more useful to write this in reverse to show what order it actually gets written in. But anyways, so we know then basically that pushes X, then B, then A. So X is actually 2 bytes followed by 1 byte, and then A in that order. So which means that in order to access these from the stack lower down here, S plus 0 would be accessing the value that was in A, S plus 1 the value in B, and S plus 2 actually S plus 2. That would be weird, wouldn't it? That would be weird because we would be reading in the middle of the byte that of the 2 bytes we wrote here. And I doubt that that was on purpose. This is probably where our bug is. I'm thinking maybe what this implies is that in fact, it should have been pushed in this order. Let me check. I mean, clearly in my push instruction, I'm doing it in reverse. And then in my pull, yeah, the reverse of that. And that's, I believe when I implemented this, that's what I read. So let me go check my docs and see if this makes some sense. So we'll look in this cookbook. We'll start with that. Push S. Let's see what this guy tells us. See, it even says it here. Y, X, B, then A. Oh, no, wait, this is fine, right? I'm getting confused, right? Like, am I? Two bytes. No, that's what I said. It would push X, then B, then A. Just like here, it would push Y, then X, then B, then A. And then pull from U, the D, then X, then Y. Okay, let me keep looking for this instruction. What was this? Okay. Okay, here's the push instruction. So, push order is from left to right. Yeah, so PCU. So it shows here clearly that if B7 is set, then both PC low and PC high is pushed. B6 is set, U and US low, US high, Y low, Y high for this one, X, D, then accumulator B and accumulator A, 1 byte. So it's exactly as I would have expected. So let me see if I can understand this code. Maybe I'm not understanding it. So push A, B, X means push X first, but then we go back. Right? Okay, yeah, no, it's okay. It is pushing that order, but the thing is that it's effectively A, B, X. Okay, that's why we write it this way. because in memory it's going to be laid out A, then B, then X. Layout A, B, X, and then 2. Okay, all right. Because the stack pointer decrements when we push, and that's why when we want to, if we want to access the what was pushed by, and here we say we could index s comma 0, s comma 1, and then this is s comma 2 for 2 bytes. Okay, so that actually makes sense. So this one nullifies that one, and then later on here, this would be loading what was stored originally, what was an x here. Now, unfortunately, I don't print the values here, so let's see if we can see above here what would have been in A, B, and X. So we know B here would have gotten D6, which is indeed what we see down here, right? Is it? Scale factor, what was it again? D6. Okay, so that confirms that we're reading D6. B equals D6. Scale factor. What else here? Load X. Load X, A, comma, X. So A would have had 8, and X would have had this address. See, what I'm wondering is maybe what we would have expected to go into X is just this address plus 8, which would have been this one here, and yet I think what ends up happening is we end up reading, we do an indirect read here and go and grab the value 34 and then the following byte, which we don't see in my output here, but we know to be 3408. And I wonder if that's wrong. Maybe we're supposed to store A plus X into X, not, what did I say? Not read what's there, which would be 3408, I think. Yeah. Okay, so let me double check here. Load X, so that's our instruction AE followed by 86. So this is index mode. This is actually difficult for me to debug without, to look it up, because index mode is so complex. So what I could do is I could actually maybe put a breakpoint on this guy and see what happens in code. So let's do that. Start all over. Set a breakpoint when we're at that instruction. Load symbols, and let's trace. Disable trace, and let's run. And when we get to that instruction, we'll debug it. Let me go back here. I mean, I'm not sure. At the same time, this address is actually an instruction address. What I mean to say is that, this would mean that the data is in the ROM, which is possible, yeah. And it's just trying to read, it could be reading the data interspersed with the code in the ROM. Because see, like anything in the E range here would be the Mindstorm game itself. So like we can see like here we're at E59F, that means we're in Mindstorm code. When we see F, we know we're in a BIOS routine. And if I'm right, that means that the data would be there. It wouldn't make much sense to be looking up what does it use X for again? The beginning of a table. Yeah. See, it would kind of make sense to say, I know that in my ROM I have this table for the draw routine that we're looking at. This draw here. X is supposed to point to this vector list. And it could be that that vector list is right there in the ROM. Okay, we've hit our breakpoint. But just to finish my thought. And then we would say load that into X so that when we do draw, the draw would basically read at that, at this specific address, and that would be the vector list right there in the ROM. But instead, I'm actually going ahead and reading that and storing the 2 bytes there into X, which seems incorrect to me. So that's my guess is that we're doing something wrong with this instruction. That's my current guess. So let's see. So we're at that instruction. I'll turn on the trace. I'll set a breakpoint. I'll set a breakpoint where I'm about to execute this instruction. So here. Step. Load XAX. Yeah, that's the one. Although this time there may be more. Okay, we might be hitting this guy more than once. In any case, okay, let's continue with this one. So here it looks like it would end up storing EE into X, which I don't think is right, as opposed to storing E25A, which I think is what we meant here. So let's see where this brings us. So we look it up. We get a load X indexed mode. That's what we expect. So there's our load X. So all looks kosher. All right. Now step into this. Read operand value 16. Let me think for a sec. I think I'm wrong. If we wanted to store the value of this, we wouldn't use load X, right? Load X always means based on the addressing mode, we have to go and compute an effective address and read from it. This is not some immediate value or something. So we are index mode. So let's see. So we read the post byte and we get this value. We look at the post byte and what do we fall into? We fall into this case here, which makes sense. Plus or minus A comma R. That's right. Comma register. So A is 0 in the specific case that we're running. And X, register select should go and read X here. Yeah, it does. And X does have E25A, as I show in my printout here. So that is exactly that, E25A. Let me check something in the doc here. Load X. Okay, so load register for memory 16-bit loads the contents of the addressed memory into the 16-bit register. And see, that's it. What I was thinking about was more like load effective address. The fact that it's a load X, not a load effective address, like not a LEAX, means we want to read there. So actually, my theory is wrong. It's doing the right thing. It is reading 2 bytes here that are formed by that address. Which is okay. Okay, so if that's true, let me hit F5. Continue here. Okay, now we're hitting it again. Oh no, sorry, we're just hitting my breakpoint here. Just stop for a sec. Let me go back to see how many instructions we've run so far. Okay, we're very close to where the bug is. 8.10.896. Well, actually not that close. So let me set my debug count here. So this way we don't look at trace for too long. Turn off the trace and continue. Oh, sorry. Trace, continue. Okay, so we just hit the breakpoint again. So this might be the second time. If I step, so actually we hit it fairly often, and now, okay, and here we go. Now we're very close to where the bug occurs, because I just hit this breakpoint. In that case, I want to break into the debugger, turn on trace, and continue. Okay, so then if that's not the problem is something else. We'll just go back to where we were. I'm trying to remember what was the actual instruction that we were running that was wrong. Okay, so breakpoint hit, so this must be the one that fails us. Trace enable step. So if I do info reg here, there it is, the 3408 that ostensibly causes us a problem. Maybe this A is wrong. Okay, so right now we're at this instruction here. Let me see. Load X, A comma X. So there we are. That's exactly where we are here. A is 8. And that's producing this address, and it's getting the 2 bytes there, which is 3408. I mean, we can even, just to be doubly sure, we can print what's in memory here. So at E262 is 34, and at E263 is 08. So that's what we're loading into X. So then when we come down here, and we jump to the subroutine, draw VLPB, which in the BIOS is this one here. And we want to do a get next coordinate pair. We're doing load D, and that's the whole point here, is we're saying into D load the value that that X points to, offset 1. So that is reading at that address, which is a weird address to be reading from. So now I'm wondering, can I find I'm wondering about those other instances of when we had this instruction running. No, yeah, because we were in the same place. See, it's possible that there's a bug with the way we compute A. Maybe that's what's going on here. Because we have 8. That means that there's a 1 bit that got shifted left into the 3rd position, right? I mean, into bit 3, exactly. Does that make sense? Look at this here. Load X E25A. Yeah, so it really wants to read at an offset from here. And then the offset is then determined by reading a value at U plus 1, which in this case was 4, which was that bit. Yeah, exactly, bit. So that's 4, and if we shift this left 1, we would get 8. This is logical and arithmetic shift left of A. Basically, they are the same thing. And so here when we load A, we're saying read from U at offset 1. So this is the user stack. So this means read something we pushed onto the stack at position 1. So there's probably going to be a push U somewhere above here that corresponds. So we have a pull S here, but that's not what I'm looking for. Let me do a search upwards, and let me also mark where I'm looking at. ABDCW asks, what are you currently doing for your emulator? So I'm in the process of implementing the CPU. That's usually the first stage. I have a debugger, and I've got a partial CPU implementation. I'm missing some percentage of CPU instructions that's less than 40%. In fact, that was the last time I checked, and since then I've implemented at least 7 instructions or so. So let's say, I don't know, let's say, I don't know, 30-something% of instructions are left to implement. I'm going to try and look at the camera when I speak. I always look at the chat, but I'll look at the camera. So yeah, basically I'm trying to implement the rest of the CPU. And the way I do that is when I run the Vectrex, the way it works is we got to run the BIOS. There's this ROM that contains the BIOS, which is all the routines that control the hardware that games will use. So I run that, and then eventually it ends up looking like it goes into the built-in game, which is Mindstorm. And so then that runs. So that's all the stuff we see here, like in the E range. And whenever, like the goal here is whenever I run, at some point I expect to hit a unimplemented CPU instruction, and then I implement that one, and then I run again. And every time I go a little further, I hit another CPU instruction I haven't implemented, and then so I just kind of do it that way, rather than, let's say, implement all of them in one shot and hope for the best. I just implement them as I need, so it just feels more like progress when you do it this way. Plus, because by doing it this way, what ends up happening is you realize mistakes that you may have made in instructions, and rather than having to fix them in multiple places, you fix them, in only the few instructions that might have had that. So it's a more iterative process, and it's a bit more rewarding. Right now, though, I'm investigating a bug where what seems to be happening is it gets to a point where it tries to load from memory a value, and it's accessing what seems to be a strange address. It's actually an address that would be in the cartridge space range, and I don't believe that's right because we are loading Mindstorm, which is the built-in ROM, and should not be accessing the cartridge memory range. If we look at the memory map here, The memory map is quite simple for the Vectrex. So it's a 16-bit bus. So it goes from 000, 4 zeros to FFFF, right? And the cartridge basically takes up the first half of all memory, so 32K out of the 64. So normally when you pop in a cartridge, at some point I suspect it's supposed to run from, maybe from 0000, I don't know. Or maybe it's supposed to jump to the last address or whatever of this range, and then like 7FFE maybe. Or probably no, 7FFD, and then read the 2 bytes there as a jump to where to start in the cartridge or something. I don't know. I haven't actually read how to implement like cartridges and how they start, because right now I'm just relying on it running the built-in ROM. So I'll show you that. So then here we have some unmapped memory in this range. We have RAM that goes from C800 to CFFF. Here, that's 2K of RAM. And we have here 16 bytes that's shadowed 128 times, D000 to D7FF. So this is for the VIA, which is basically the chip that the CPU talks to for interacting with all the peripherals. So with the vector ray, how to control the vector ray, how to poll input, how to play audio, all of that happens via this chip, via the VIA. And then there's some RAM here, which you're not supposed to access, where both VIA and RAM are selected. And then finally, we have here 8K near the end, where the first 4K is for this game, Mindstorm, which is a built-in game in the Vectrex, and it's actually like an Asteroids clone. And then the last 4K, starting at F000 to FFFF, are all the BIOS routines. And the way it bootstraps the Vectrex is you actually jump to F0000 and you start executing from there. So in fact, you can see that in my main here, after I create everything and plug everything together, CPU, VIA, RAM, cartridge, debugger, all this stuff, I load this BIOS ROM, which is an 8K ROM that fills in the space from E000 to FFFF, logically in terms of memory map. I'm loading a cartridge, but I'm not technically using it. And then here we see the BIOS routines start at F000. So I tell my CPU reset. I say reset and I give it the initial PC, the initial program counter. So it points to F000 and then we begin. So all that to say that I get now to a point where I have an instruction that's trying to read out of the cartridge address space, which is odd. In fact, what's really odd about it is I'm loading a cartridge right now, and the way I've coded it is that I think I'm loading one called Scramble, so I can show you that in here. ROMs Scramble. See, so this cartridge is actually 4K. It's 4K, and what I do is I basically allocate that much memory in terms of like address space for the cartridge. I expect all accesses to go from 0 to 4K and not outside of that. But I'm actually getting an access outside even of that range, which makes it even more dubious that that is valid. So, yeah. So where I'm at now is I'm trying to understand how come, like why is that address, where is it coming from? This address that is out of range. So the address that I'm interested in is 3408. Here, 3408. That's what gets effectively loaded into X. We call this routine called draw VLP B, which is a drawing routine in the BIOS. We can tell that because when we jump to it, you see we're in the F range. And in fact, I have the BIOS here. So this is the function, draw VLP. This routine draws pattern lines using the vector list. So that's draw vector list, P for patterns, I don't know, pattern lines that are pointed to by the X register. So this X register is supposed to point to an is a pointer. It's an address to some data in memory that has the following format. It's got like pattern, rel y, relative x, pattern, relative y, relative x. So I think what this means is this is a bit pattern. It's a byte that has like zeros and ones that tell you how you want to draw that line. And I think this here means where to move the beam where it's currently pointing at, where to move it to relatively from where it currently is in Y and in X. And so you can basically write, let's say you want to draw a box of a line, like just a line, right? Solid lines. You'd want your pattern to be all ones. And then you could say have 4 of these to draw your 4 lines where you specify, go, let's say, nowhere in, let's say we're in the top left or something, and we say don't move in Y, but move some distance in X. Then we say now, draw the same pattern, but go down in Y, but don't change X, and then left and then right, and you will get a box. And then you have to end with this in the data stream. So X is supposed to have this address of this kind of pattern. But the address that we're getting is in that cartridge range, which seems odd. Just looking here, you see how this code actually starts by saying take X and read the next coordinate pair. So it's saying read at offset 1, byte 1, so it's saying skip this, and then read 2 values into D, because D is actually a 2-byte register. So in fact, D is both A and B. So A will contain relative Y, and B will contain relative X. Because I see here actually afterwards it says store into the via port A, the value in A, which will means store Y, send Y. And then after that, clear in port B, and then we should see it also reading B, or storing B. Yeah, there's store B, so send X. So all this makes sense. What doesn't make sense is that when it reads at X plus 1, X is that invalid address. So I'm kind of working my way backwards to say, so how does X get this invalid address, and does it make sense? So that brings me up here. So I have this trace of all the instructions that led me to that point. And I am now here. So, okay, so X, right? Like as I said, X is getting the value 3408, which I believe to be the weird thing that we're getting. It doesn't make a lot of sense to me. So I'm saying, okay, so how does X get that value? And it gets it on this line here. This is where we load X. We load X by saying, load X by reading from X comma A. X comma A is computed here by saying take the value in X, the address in X, add 8 to it, which is the value from A, build an effective address from that, which is here, you can see it. So it's 25A plus 8 gave us 262 here. So E262. And then read the 2 bytes from there. And it's read 2 bytes in big endian. So it's 34 in the first byte, and we're not seeing it, but it's 08 in the next byte. That ends up in X. And so this here, this bit that's in X at the moment before we load X, comes from this load up here. So this here is loading this immediate address in there. So this here does not seem to be the problem. This is saying, to me anyway, like the game is saying, I know that the byte pattern starts from here plus some offset. And that offset is an A. And so to compute A, what it does is, and that's where I'm at now, is it says, well, load A, what's in U, comma 1. So when you see this pattern here, U, comma 1, U is the user stack. So it's kind of like 2 stack pointers in the Vectrex. There's the system stack, S, and the user stack, U. And there's basically push S, push U, pull S, pull U. So you can use either one. And I think the idea is that the system stack, S, is going to be used, let's say you call BIOS routines and the BIOS routine calls other ones, it'll keep using the S for that, and that the user stack pointer is basically for you. It's a separate stack that you can use. So anyway, in this case, we are loading A with whatever is in U, comma 1. And what this usually means is it means that there's a push earlier on U, and we are reading 1 byte into what we push. So it's like if I was to push 3 values onto the stack, I want to read the middle value from what I last pushed. And here, what that looks like it's turning into is saying, well, U right now is C933 plus 1, which is C934. So this is where the user stack pointer would be pointing at this moment when this instruction executed. Offset by 1 is obviously C934, and what's the value there? It's 4. So that means that somewhere up above we pushed 4 on the user stack. And then we take 4 and we shift it left. We do a logical shift left, A. Just want to check something here. So logical shift left. CPU. So it's the same thing as arithmetic shift left. And in this case, 48. So it's this one here. So yeah, it's really just a shift left by 1. You don't actually tell it how many bits to shift. It's an inherent instruction that only shifts left by 1. We can see that if I look it up in here. LSLA, so LSL, logical shift left, shifts all bits of accumulator X or M 1 place to the left. It also actually shifts into the carry. So it's really it's treated as a 9-bit 9-bit value, where carry gets shifted into bit 0 and bit 7 gets shifted into carry. Which doesn't matter here for us. What matters is that we have 4, and when we shift that left 1, it becomes 8. And then we end up reading at an offset of 8, and we're getting this 34. So maybe that's wrong. Okay, so if I continue down this line of reasoning, my next question is, does it make sense that u has this value? So let's try and figure that out. So u, look for push u above to see when what? When 4 got pushed there. Okay, so let's do that. So I'm going to move up from here, push u. Hopefully I have it, and I don't. So that's interesting. And I mean, the problem here is that, you know, I don't have all the instructions. I basically stopped at about 6,000 instructions before my problem. So I might need to just run this again and get more into my trace so that I can find. But that's interesting. It means that this values on u were pushed quite a bit earlier. But maybe that's not so much of a surprise, because when I look here, this code here is some kind of loop. Very repetitious. We can see as I move up, it's always the same. So we're in some kind of loop here. It's probably just some function call in the BIOS that just loops and loops and loops and causes a big mess of trace before we actually get to something interesting. So in fact, so you see here, we have a return from subroutine from a BIOS routine back into the E, so back into Mindstorm. So let's see if I can find the previous. So that's intensity 5F. This is all E stuff. E. Random. Okay, so we're calling the random subroutine here, which runs a bit of code. Then we keep going. Then here we call random again. We're back into the E range. Then we call rise run Y here. Is that, no, that's not our long function. We return here. So then we have a dp to d0. Yeah, so this is the repeating pattern. We're always coming back to E64F. Or not? Or is it this guy here? Oh no, okay, so that's not the repeating pattern just yet. Okay, so there's actually a call to the draw VLPB that we're looking at up here. And then again. So it's this call that's being done over and over again. That's very interesting. Very interesting indeed. This code keeps repeating. So now I wonder, and then we're repeating it, and then at the very end, we're getting one that accesses out of range. That's interesting. So this could mean that we're calling this function. So either it's valid and like we're just calling this function to draw multiple vector lines for different ones, or maybe we're calling it and then it's somehow we know that like the program thinks it failed, so it's calling it again, and there's some kind of reason why it's failing, which is why we're calling it again and again, and we eventually end up seeing the result of that failure as an access into invalid memory. So that's another potential. So what I can do is try to diff consecutive calls to here, just to kind of get a picture of what might be changing between the calls. So let's say I open up my compare tool, beyond compare, come back in here. So we'll grab this very first one. Actually, I can do begin and select here, then go to the next one, begin and select, and then finish the selection here, and we'll put that actually above here. We'll put that in here. And then for the next one, we'll start here, edit, begin and select, go to the next match, select that one. Okay, the diff tool did some weird alignment stuff. Oh, maybe I over-selected. Let me just try that again. $430. So 430 to 810. And the next one is 811 till 950, which, yeah, seems a bit short. 430 to 810, then 810 to 950. Or maybe it makes sense because, if these are all valid calls, then it could just be that what we're seeing here is that, the first one had multiple lines to draw and the next one had less lines to draw. So that's perfectly legit. But let's just get like an idea. So in fact, 950 to 1105, that's about 200. Yeah, these may just be perfectly valid ones. So that's 430 there. So let's try again anyway. So 811. I already did a begin there, but let's just do it again, just to be sure. Begin to 950. Okay, so yeah, the lengths are completely different, and it's doing some weird alignments here because of that. And I can try to help it a little bit. I'm just trying to align these lines together. But yeah. So let's see, can we get a little idea of what's going on here? Yeah, we can see clearly that x is different. And in fact, I'm kind of interested in this x line, because this shows us what kind of addresses we usually get and what kind of values we usually get at those addresses that get stored into x. Unfortunately, I don't actually print the full value of x here, but later on when I read x, I should be able to see it. Like here. Load, so load x plus 1, so x had EF04. See, EF04 makes way more sense as the address that would have been stored into x. Okay, so let me actually, just for information purposes, let's print all the times, all the instructions that all the instructions that load this x1 within the draw routine, and see what kind of addresses we're getting. EEBB, EEBE, EEC1, C4, C7. So here, what this tells me is what I suspect is that, so what I was suspecting is that, like, when we draw, normally we should be storing into X an address that is within the range of the ROM. Like, the data is in the ROM, so it's in the EE, like in the E range. Whereas when we finally get down here, we don't have a print line for the call here. It would have been coming up, but it would be printing. It would end up printing here as though the load 1 comma x would give us an EA of 3408. Okay, so that's very interesting. If I take this first hit here, what I'm wondering is the code running up to the draw call similar to the code we were looking at before? It looks similar. I mean, can I duplicate this? Clone to other view. Okay, there we go. Let me go back down here. Yeah, so in the run up to the call, which is here and here, no, it's not quite the same at all. RTS. Oh, no, sorry, it is. I'm getting confused. Actually, EA88, EA96, yeah, so it's not the same. It has the load B1S here, but it's not touching X. Whereas here we are touching X at EA96. So let me take a look at something else here. These calls, if I search for the calls here like this, all in document, just looking at the addresses at which they happen. So we have one at E888. Now we have a few at E888. We have a few at E77F. And then the one that crashes is the one that's causing us a problem is at EA98. So the one I'm currently looking at is different from all the other calls. It's happening in a different place, and it's one where X gets loaded before the call from S, from the stack pointer. Whereas in the other cases, where is X actually coming from? So, okay, so we're pushing it here. So we're pulling it up here. So it looks like the last value would be whatever was pulled here. Oh, that's a push and a pull here. Here. No, not yet, but we can see that X here was FC6D. That does not correspond to what I was looking for. Oh, here, pull S XPC. Okay, so that would have overwritten. I'm thinking it would be really useful for me in my debugger if I show the values that end up getting read, that are going to be read, I mean, from the pull instructions. And even showing what gets pushed when we do a push instruction would be useful. Just more information. So C8, D7 up here. So by here, X became FC6D. Ah, here it is, the load X. Okay, I shouldn't be searching for a whole word. And I am not. Why didn't it show the load X? I guess that's just the way this guy works, okay. That's too bad. So there's these loads. C933. So now what I'm wondering is, since this is not the same call, where is it? This one here. Coming on to EA98. Am I getting this? Am I reaching this only once and then crashing? That's what I'm wondering right now. Let's find out. Because what I wonder is, do I actually have some code, like, do we ever reach this address and run the call and it works. And then now we have a case where it's not working. Also, I need a longer trace because in my trace I'm not seeing, I'm never seeing basically the problem, like where that U comma S, sorry, the U comma, where is it, U comma 1 here, where this value in U came from, I believe. Is that true? Maybe I was just looking for the green, but that's not. Yeah, no, it is here. Load U C933. That's C933. Let me just check something. Does that make sense? It does, right? C933 falls into this range, which can be used by the programmer. So it's, yeah, that's perfectly fine. So the user stack can definitely be pointing into there. Okay, that's good. So if I come back up here, so C933, and then what happens is that C933 and oh, sorry, it was up here. C933 offset by 1 has this value 4, which then gets shifted left by 1 for whatever reason. So that would mean that the question is, why is the value 4 there? What if I'll find C933 above? Interesting. So here, at an address at some code a bit higher, we have here a load effective address Y, which ended up loading C933 into Y. And at that moment when it did, it had 20 in there. So 20, which is 32, which seems like interesting. So if I had 32, and we shifted that left by 1, we'd get a much bigger offset. We'd get 64. Okay, so what happens with this value that's being loaded? It's loading that one here. Because really the next time is when we load into U here. So probably what's happening is that we have some code that's going to be writing values at Y after here. Decrement 8F. Okay, so that just goes and decrements some value at this address. We don't care. Branch if not equal to EB4F. We don't. We return. So does Y get used to do some writing after this point? Not really. So what was the deal with this? So it kept loading it. C91F, C929, C933. Constantly decrementing this value at 8F. Then it became 0. Why was it doing that? It wanted to load this value into Y by the time this routine finished. And it jumps to some other routine. So somewhere we want this Y. Yet the next time I find Y in the instruction stream, in the trace, we're actually loading it with a new value. So maybe what we're seeing here is some kind of stomp. It had 20 there. It can be so many things. It had 20 here. It was maybe supposed to do something with Y and it didn't. Maybe what ends up happening is some other instruction is writing to memory like near here and ends up stomping this guy with 8. What I would need now is a hardware breakpoint. I'd want to stop here and then see what afterwards what ends up like stopping whenever this address gets written to. Let me make some notes here. So Y gets loaded with which is what U is loaded with as an immediate value later. This Y doesn't seem to be used, even though this routine looped until Y was set to it to do. Stop here, then hardware breakpoint on this on C393 to see what modifies it. It becomes 8, which, no, actually becomes 4, sorry, which might be our problem. Gets shifted left by 1 to become 0.8 and is used as an offset so for an offset to read to get address of what table for drawing Y, I forget the name. You get the address to offset of table to store in X when calling. Okay. Just to make sure it makes sense what I'm saying. So if I search for this, this is when it gets loaded into U. Okay. Also has the value 20 here. Also, it didn't change until, here. Interesting. Still at 20 here. Ah, because it's u plus 1 that we're interested in. I was following the trail of what of C93, okay, of u, but it's u. Okay, so actually, I don't care about what I just wrote. Yeah, I don't care. It's this one. It's this 1 byte offset that I care about. So interesting, up here, okay, so this is very early on. We can see that this memory had, like at this address, it had value 0. And then by the time we read it here, it had value 4. So it's like at line 336, by 6026, it had 4. And I'm not seeing any, at least not in my comments that I produce, any other place where this guy gets referenced. Here we're doing store A, 1 comma u. Oh, no, sorry. I'm getting confused. Okay, so this is where the 4 comes from. This here is showing the value before we write. So it had 0, now has 4. Okay, so that's where the 4 comes from. Interesting. It's actually explicitly loaded there. So we load A with 4, we store at u comma 1 the value that's in A, which is 4. So that's where that 4 comes from. So that's valid. And then that gets shifted left by 1, it becomes 8. So let me just erase this, this is garbage. Okay, here. So that's the 4 that we saw. And then it shifts left by 1. Become 8. So really maybe what I should be looking for is why is there 34 written at E262? All these jump to subroutines show this value in the comments because my debugger, I just read the value that's at this address and show it here, which happens to be the first byte of the next opcode at that place. For example, here 34 is 34. It corresponds to this push S. So that's just noise. So yeah, I have nothing that shows me when this happens. So really what I want most likely here is to put a hardware breakpoint on E262. Hardware breakpoint on write to E262 and E263. Okay, that I will have to do next time because I'm getting tired. It's midnight. those of you still watching, thanks for hanging out, for watching me try to debug this. I know it's not the most exciting thing, but one thing for sure is the more I do this, the more comfortable I am getting at reading this assembly language, which is really cool because when I started this emulator, I did not know this assembly language at all, and was really stumbling. And in fact, is the reason why I even implemented this part of my disassembler, showing what each instruction even means. But every time I have these bugs, I spend some more time looking at traces like this and trying to understand it. When I'm in the BIOS, at least I can cross-reference it with the BIOS and understand it a bit further. But this helps me, like looking at the BIOS routines with the comments, also helps to gel into my brain what these instructions usually mean, or how they're used. So that's really cool. So yeah, then the more I do this, the better. The more I learn how people programmed this processor. So yeah, next time what I'm going to do is I'm going to implement into my debugger the ability to set hardware breakpoints, even if it's really rudimentary, but just a way to say, hey, when there's a write, I can do read, write, or both kind of thing, but in this case I want to know when there's a write to here, can we stop? And I want to see where we're at and then get a trace for that code and see if it makes sense. Because it seems to me that it doesn't make sense that we're getting a write of 3408. Because that's just a strange address for us to be then later on looking at for our table. So yeah, why are we storing 3408 there? This is a weird address for where the table of values for whatever it's called should be. Okay, so I'm going to stop here. Thanks a lot, guys, and I'll see you next time.